All right, should we start? Okay, so before I get back to the kinematic space for this scalar theory, I just want to do one more thing at the level of pictures. The remarkable thing, we've erased this so many times now, it looks like a Frankenstein monster. Sorry. Tadpole for Halloween, I guess. But, so what was remarkable here was that if we look at the, just to repeat, if we look at the pattern of consecutive the pattern of poles that can come together that you discover in the tree amplitude, it's a remarkable fact that that sequence of pole patterns is associated with the facets of this polytope. That's not supposed to be obvious, it's a remarkable fact. And as I said, this, once you know about the polytope, you also know about factorization because the polytope factorizes on its boundaries. Okay, so as you saw, do you remember from yesterday, the isosahedron for n equals 4 is just an interval. The association for n equals 5 is a pentagon. This is the isosahedron for n equals 6. Is the picture that we saw, and you see that this picture has 6 faces that look like pentagons. Those 6 faces that look like pentagons are exactly the factorizations of the amplitude onto 5 point times 3 point. And so the fact that it looks like a pentagon is exactly telling you that on this facet I'm getting this guy times nothing. N equals 3 is just nothing, is the point, I guess. And then these 3 square faces are the factorizations into a 4 point and 4 point, and that's just the statement that the direct product of 2 intervals is a square. Okay, so this picture actually knows everything. Not only that there's that the combinatorics of the poles that can occur together is polytopal, but also that it actually factorizes on the boundaries into the product of lower pieces. Okay, so what I wanted to just quickly do is just to see how much of it is this somehow an accident? It's kind of a beautiful thing, but is it an accident? I just want to motivate what these pictures could look like at beyond tree level. And let's actually look at an example at one loop. Let's just go to one loop. I'm just going to draw some pictures. But remember, what is it that we're doing here? What we're doing here is that all we're doing, whatever else is going on in the graph, whatever else is going on elsewhere, we're saying that a vertex can be connected to another one by this sort of elementary move on the inside, right? So I can merge something in the S channel and blow it up in the T channel. All of these vertices are connected locally by moves like that. Okay, so let's just ask, could there be a similar story at one loop? And let's begin with the simplest one loop diagram. Okay, so the simplest one loop diagram is kind of a bubble. We don't draw that at tree level, it's just a line, there's nothing to say. But already here at one loop we would draw a bubble. And so let's just think, if we're imagining in terms of, if we're drawing a dual graph, there would be a point in the middle here, there would be an external point there and an external point there. So there are sort of 2 obvious propagators, right? And so if there's any kind of space associated with this, it should be 2-dimensional. Okay, because the dimensionality of the space is the number of propagators. All right? Now, let's see, where could this guy go to under one of these kind of flip moves that we had talked about? So here, what we could do is we could take this picture and we could shrink this propagator and blow it back up. Right? So that's one obvious thing we could do, and that takes us here. Okay, so that already gives us this funny tadpole diagram. Now, this is something you've got to get used to in this business, that there are things as physicists that we are so singular that we tend to be either scared about them, or we throw them out, or we don't care about them for a variety of reasons. Actually, even this bubble, let's say it was an external line, you might be tempted to get rid of it. You know, it's a massless bubble. If you integrate it to 0, or it's 1 over epsilon minus 1 over epsilon, or whatever, certainly this tadpole sucks, right? This tadpole is just garbage. We don't like these tadpoles. It's the cosmological constant problem. Okay? We don't like them for both technical and phenomenological reasons. Okay, but somehow you can't just willy-nilly throw out the diagrams you don't like. Okay, because they're related to each other. You can sort of get there, and if you just think for a second, if we want some kind of structure that's going to factorize when you put some internal propagator to 0, I can't just throw out this tadpole, because that's part of some 4-particle amplitude that's inside that has that T-channel piece in it. So I can't just sort of throw it out. So that's a 0th order thing. You've got to get used to the fact that there's going to be weird things like tadpoles floating around. You've got to know what to do about them. And let's just see what the problem. So I can go from here to there and back. Okay, and I can also go backwards from here to there. And I get the tadpole on the other side. Okay, and now we have to figure out. There's a last thing that I can do. So in other words, if I take this variable and I mutate it, it turns into this one. If I take this variable and I mutate it, it turns into that one. Now we have to ask what. Let's say I take this variable. If I take this variable and mutate, I go back. Similarly, I take this one, I go back. But what happens if I mutate this variable? Okay? And now comes the difference between fancy cluster people and physicists. Okay? Fancy cluster people invent a new kind of object, and they call them tagged arcs, and off they go. Okay? And physicists just do that. They say flip the tadpole. Okay? Okay, so I'm just bringing this up because this is not the cluster thing, right? And it may well not work in general. It may well not work. It may not well work beyond one loop. But this is at least a rule that we can talk about and see what it does for us.
But this is exactly a cluster.
Well, it's not a cluster mutation. It's not a cluster mutation. You have to, because I'm not changing the identity of this guy. I'm not doubling it. You will see precisely how it's related to the cluster picture in a second. That's why I left the association out there. Okay, so I'm saying this also partially to encourage the physicists. I mean, it's wonderful that we have wonderful friends who are mathematicians, but we're our own people too. Okay, so we're allowed to do stuff. We're allowed to do stuff. We don't always have to do what they tell us to do. In fact, maybe we shouldn't screw them. Okay, so let's now keep going with this picture and see what we get if we do this now at 3 points. Okay, so if we do this at 3 points, I would start with a picture that looks like this. Okay, and let's see where I can go from here. Okay, so where can I go from here? Well, from here, I can mutate each one of these guys, and there are 3 places that I can go. So if I mutate this, I can maybe go to something that looks like that, or something that looks like that, or something that looks like this. Is that clear? Right? So I can shrink this. Which order did I do it in? I guess here I shrunk that guy, and I opened it back up in this direction, and I'm doing the other ones as I go around. Okay, and now what do I do here? See, now if the new kind of things that I can get if I don't go back from here is, well, just what I had before. So I can get like a tadpole on one side, or I can get a tadpole on the other side. Okay? And so similarly, this is going to go down to 2 things that look like that, and that's going to go down to 2 things that look like that. Okay? Okay, so but now exactly these flips that we talked about are going to allow us to go between these guys at the bottom. So I have these 6 guys at the bottom, but I can actually go from the 6 guys by flipping. That's actually why I drew this picture, because in fact, this sequence of things that we get also fits on the icosahedron. It's kind of cool, right? So I can erase all of these things. I don't need the guys at the bottom. That's the point. So here at the top, I can put this guy. Okay, and here I can put this, or I can put this, or I can put and then I can put these tadpoles now at the bottom. So like from okay, and all of these pictures actually, if I just stop here and I just take this top half of the icosahedron and I just connect the 6 things that I see at the bottom here. Now the picture got kind of complicated, I apologize. Okay. Then I can slice this icosahedron in half. At the bottom, I have these 6 vertices that are all the tadpoles that can be on either side of the line. And then here I have the bubbles on the external legs and the honest triangle at the top. And so this captures the combinatorics of the cubic diagrams with the rule that for how I flip the tadpole that I just defined. Okay? And this is not an accident, because this whole thing, as we'll see in a little bit, the story of tree amplitudes, the fact that it fits on the icosahedron is an accident, but the story of tree amplitudes, so this is just an aside for the moment, this is just to convince you that it's possible that even one loop combinatorics is polytopal, but now this is this sort of interesting polytope where I slice the icosahedron in half. It has a face that looks like a hexagon, and then at the bottom and the rest of them at the top. But as we'll see in a moment, the tree amplituhedron is associated with the icosahedron, which is the cluster polytope of type AN. And actually, for all the finite type cluster algebras were associated with Dinkin diagrams. The only ones that have an N that you can naturally associate with amplitudes for any number of particles are B, C, and D. And we'll see that all of them have interpretations in terms of scattering amplitudes. Okay. B and C are kind of in between. You can think of these as phi cubed by adjoint phi cubed theory plus a dilaton. Okay, so, or tadpole emission. I won't say much about this, but dn is really one loop. So honest dn is one loop. And in fact, if I'm doing, if I'm careful, if I'm really doing n particle scattering, this would be an minus 3 for the cluster polytope, but literally dn. Okay, so dn for one loop. So you see, for example, that for n equals 3, one loop, we would say it's D3. Well, D3 is the same as A3, right? Just that big diagram is the same as A3. And so we're saying that the cluster polytope is the same as the icosahedron. Accidentally, completely accidentally, the cluster polytope is the same as the icosahedron. And that is the entire picture here. Okay, so there's an entire picture that, with the cluster way of doing the mutation, tells you to keep going on the other side and double all the variables relative to what we talked about before. So for every sort of propagator upstairs, there's a mirror cousin downstairs, and that's fine. And that's what the cluster polytope tells you to do. Okay, but the dumb thing you would do if you didn't know about any of this is sort of half of it. So there's a way of slicing this object in half that gives us what we call dn bar. So there's a natural symmetry associated with the dn cluster algebra, basically interchanging those two antennae. And so dn bar is the sort of dumb one loop polytope. So it's the sort of slightly more efficient one. Okay? So I'm just bringing this up just so you see, this is not supposed to make sense yet, but just so you see that if you were very naive, you would build a polytope, but it would not be the one that you get from the full cluster algebra, although it's related to the one that you get from the full cluster algebra in this interesting way by cutting it in half. Okay, so but that's just mostly, and you can do an exercise for yourself to see what these guys are. These guys, when I say they're a dilaton emission, or you can think about it just as amplitudes where part of the diagrams are planar, but you're allowed to emit just any tadpole. Okay? So you can think of it either as attaching a tadpole or as just emitting a colorless particle at tree level. So if you're a string theorist, you would think of this as like inserting a zero momentum closed string or equivalently, a tadpole diagram for the open string theory. In any case, if you just take the combinatorics of all the diagrams that include these tadpoles, where you then have to decide that you're allowed to flip the tadpoles around as you go around, all of those guys are also polytopal, and that's what's associated with the intermediate guys, the BC type. Those are called cyclohedra. Okay, so, but you could just discover it yourself. If you do it at enough points, you could try to build these pictures. For example, if n equals 3, it's obvious to get a hexagon, because I just start with the 3-point guy and I just put the tadpole on one side or the other, and I can flip them around. Okay, so that's what I get. A hexagon, if you go to 4 particles, you get a 3-dimensional shape, and it's a quite intricate, beautiful 3-dimensional shape you could just discover for yourself. So in all these examples, tree, 1 loop, tadpole emission, 1 loop, just playing with the graphs, you see this fact that there's a polytopal structure. So the kind of poles you see is there. And now we're going to see none of this is an accident, but I just wanted to stress the part that you could discover for yourself by playing. Yes?
And so the D2 is actually A1 times A1.
Yes, D2 is A1 times A1.
How are these actually connected? So
yeah,
it should be a very simple.
That's very good. You see, what I drew for you was this picture. Which is a triangle. Okay? And A1 times A1 is a square. And again, I'm cutting the square in half. I'm cutting the square in half to get this triangle. Okay? And if you're a cluster person, you've got to mutate to another kind of variable. That's this business about the tagged and untagged variables that Lauren was talking about last time. And so at least in this small case, there's something else that you can do. The reason I'm bringing this up is that here it's a minor. You might even like it. In any case, it's not. It's a sort of minor difference between the stories. I'm bringing it up at this level simply because if we later get to talk, which we probably won't today, if we want to talk about extending these things beyond 1 loop, 2 loops and higher, now the difference between what the cluster person wants and what the field theorist wants starts becoming really extreme, because now you get into this world of infinitely many cluster variables, because we want to slavishly follow the rules of mutation handed to us by the cluster gods. You have to keep getting more and more and more cluster variables, which have absolutely no purpose in life in physics. Okay? So this seems like a very baby version of that phenomenon, where we don't have to introduce infinitely many of them, but there's something that we're allowed to do, which is not officially a mutation. Okay? It's not officially a mutation. In the association picture, it cuts across the square, right? It's 2 mutations. It's not officially a mutation, but it's still something canonical and natural and well-defined. And we're probably not going to have a chance to talk about it, but I wanted to mention it at this point already. We would love to find some way of taming the infinity associated with the cluster algebras associated with surfaces. The cluster algebras that Lauren talked about yesterday associated with surfaces with punctures on the inside are exactly going to be associated with general multi-loop Feynman diagrams. So that's the cluster structure that we care about at all loop order. And we're struggling for a while to try to find some way of making sense of that. Okay, so, but the sort of basic tension is that there's something that's natural from the cluster point of view that's not natural from the point of view of the amplitudes. And it would be very, very beautiful if there was some canonical way of dealing with it. Anyway, that's just an aside. It's not supposed to make any sense if you don't know what I'm talking about. Okay. So now let's finish playing with pictures, and I want to go back and think about our kinematic space. First thing I want to do is think about kinematic space. And so our kinematic space, remember, is a space of all these xij's, right? Just the diagonals of the polygon. Okay, but I want to begin in a very, very simple way, just by trying to just write all these variables down. Okay, I just want to represent all these variables. Like what are all these variables? Like x12 is like 0, for example. I don't have it. That would be, so I would actually set it equal to 0. It would naively be the mass squared of particle 1. So x12 is 0. But then I'd have x13, x14, let's say, x15, say 6 particles, x16, and so on. I have x23 is 0, x24, and so on. Okay, but no, I just want to like arrange all these x's. I just want to visually depict all these xij's. And there is a tiny challenge, which is that the xij's have a natural cyclic symmetry acting on them, right? I want to cycle everything over by n, and yet I have ij and ji labeling the same thing. Okay, so let's see how we can represent this in a nice way, and I'm going to do it in the following way. My choice to draw things on 45-degree lines is just because it's going to make it easier for later. So this is just denoting the variables, nothing else at the moment. Okay, I just have x12. I'll draw like this. x12, x23, x34. Let's do n equals 6. x45, x56. And so here's the problem. This is x61. Okay? Let me keep going. So here I would have x13, x14, x15. x16, and I would have, so it's clear what I'm doing, right? x24, x25, x26, x21, and so on. So you see, I have this mesh. It goes on and infinitely in all directions, if I like. Okay, but in this mesh, when I naturally write the variable so that the cyclic action is manifest, then I'm double counting more than just by cyclic rotation, right? I'm getting 1, 6 down here and 6, 1 up there. Okay? So let's draw this picture in the continuum. In other words, imagine that I had infinitely many particles. So I just have a whole stack of all these x's. I'm just drawing this picture to keep track of all the x's. Okay? So in the continuum, what do I have? So I have this sort of infinite strip. And now I'm going to give these directions names. I'm going to call this a time direction, and this is space direction. Because that's, I'm drawing things on 45-degree lines that I'll soon be interpreting as light rays. All right? But right now, this is just I'm emphasizing, soon we're going to talk about the two-dimensional wave equation. We're going to have a two-dimensional space, and I want to emphasize where the 2 is coming from. The 2 is coming from the fact that we're labeling the chords by ij, right? The fact that we have these chords labeled by ij. But on top of that, we have this interesting identity. We have to identify this point xt with 1 plus x and 1 minus t. Okay? So that's exactly this sort of identification between xij and xji in this picture. All right, so if you want to talk about the actual kinematic space, what you want is to just pick one representative, right? So in this whole infinite mesh, I just want to make sure I get one of xij for everybody. So I either get x16 or x61, x35 or x53, but only one of each. Okay? And so a very simple way of doing that is to just cut out of this picture, pick any curve you like here, translate the curve over by 1 and flip it over. So if this is C, this is C tilde, just translating it over by 1 and flipping it over. And so this is going to give me some area 1 region in here, if this is 1. Okay? And all of the xij's will be in there once and only once. So if I go back and discretize it, this is just making sure that I'll either get xij or xji. So for example, the simplest thing I could do, well, there are two very simple things I could do. One of them is to just do that. And another one I could do, which is the one I'll start with, is this. So I'm just going to look inside this region. Okay? So all we're doing is drawing a picture of our variables. Nothing has happened yet, right? We're just drawing a picture of our variables, but it's amusing that in order to try to describe the variables in a way that takes into account this ij is ji symmetry and the cyclic symmetry, we're naturally led to drawing this sort of infinite mesh and carrying out of it this piece bounded in this way. Let me say this one more explicitly then. So if we go back to our example with n equals 6, what am I talking about? I would draw this picture. So and I would say this is x12, which is 0, x23, x34, x45, x56, and then x13, x14, x15, and x16 at the bottom. And anyway, so off we go, right? So everything is contained in here once and only once. So, okay, so you see that there are 9 points here. There are 9 points. These guys are 0, so let me, the guys that are 0, I will color. So these are 0, but apart from them, I have 9 points on the inside, and those are exactly the 9 diagonals of the hexagon that I was talking about. Okay? And with this picture, actually, it's fun that on the same little diamond, I can denote my kinematic space for any n, right? You just give me any n, I draw the same picture over and over again. All I do if I want to go to more n is I just add one more thing that looks like a light ray that bounces off the top of the picture, right? So we're starting to see, I mean, this picture, if I really call this time and this space, I'm just shooting out light rays. This is the boundary of some causal diamond. The whole causal diamond would sort of go up to the top, but I'm cutting it off with some spatial surface in the middle. Okay, and then all I'm doing is shooting light rays out from the corners. And for any n, I just plunk them down all on the inside. I shoot the light rays out, and I fill the inside of the spacetime. Okay? And then all the points that I get on the inside are just representing my kinematic variables. Is that clear so far? Nothing has happened yet. Okay, we are just representing the variables in a somewhat evocative way. Okay, but it's motivated by the desire to describe it in a way that that manifests a sort of cyclic action on this pair of indices, which are also symmetric. Xij is xji. Okay, any questions about this? Yes?
There's also the
Yeah.
space of this upper triangle and matrices.
There's no matrices here. These are just, I mean, this is just, I'm just denoting the variables. Okay, I'm just, but I'm motivated drawing this picture. I mean, it's the dumbest thing. The variables are xij, so obviously I'm going to associate them with some lattice, right? But there's a cyclic action on them, and ij is the same as ji, and that fact is what tells you that you have to be careful if you want to do this. You want to represent this with a cyclic thing is obvious. You draw this big mesh, but they're repeated. And then if you want to make sure you pick one of them out, you have to take these interesting chunks out of it. Okay? And so this is what we've done in order to just make sure we're covering every index once and only once. There are other ways of doing it. Okay? I could take other chunks out to do the same thing. This is just one particularly nice picture. Okay. I should say that this stuff is now work that should hopefully come out soon with Song and Hugh Thomas and Giulio Salvatore. All right. So now I want to go to this picture, and now we're going to do something a little more adventurous. Let's completely forget. So this is our sort of kinematic space. We can fill it up as much as we want, no matter what n is. But now I want to ask a question on this kinematic space. Okay, so I want to, remember that's our goal. We find our kinematic space, and we have to find a question to ask on the kinematic space. Now our kinematic space naturally has this 1 plus 1 dimensional Lorentzian structure associated with it, just the way that we've drawn. So the question we're going to ask is to solve the wave equation. We're going to solve the wave equation on this 1 plus 1 dimensional space. Okay, so what is the wave equation? It's dt squared minus dx squared capital X. And I'm going to solve it with a source I'll call little c. Okay? So this is time and space. And we can also use the kind of usual light cone variables u and v. And I would write that as du dv of capital X is equal to the source c as well. Okay. So again, now we're making a guess for something to do on kinematic space, right? Now we're in kinematic space. On this kinematic space, we're going to solve the wave equation. All right, now let me summarize some things about the wave equation in 1 plus 1 dimensions. First, it's very easy to solve. But the reason it's so easy to solve is that there's a beautiful, this is the differential equation, but there's a beautiful Gauss's law for the wave equation in 1 plus 1 dimensions is simply the following statement. If you give me any solutions if you give me any causal diamond, so a causal diamond is just something where the light rays go out in 2 directions up to some point, then you reverse them at some other point. You give me any causal diamond, and I have and the values of x here are, I don't know, xa, xb, xc, and xd. Then Gauss's law tells you that xb plus xd minus xa minus xc is the integral of the current inside. So I'll call that some capital C. Okay? You're used to the fact that Gauss's law is an integral on the boundary, but in Lorentzian signature, you get nothing from the edges and only something from the corners. And this should be obvious because if you take this diamond and make it infinitesimally small, it goes back to the wave equation. Okay, so this x plus x minus x is exactly this double derivative du dv. Okay, so this is the integral form of the wave equation. In the sense it's a more fundamental statement. Well, they're all equivalent, but this integral form reduces in the small diamond limit to the differential equation. Okay, so that's one fact you need to know. Another fact that we're going to need about the wave equation is which we'll use in a little bit. It's just a very simple fact. Let's say you have a solution to the wave equation, which out here is some x right, and back here is some x left. And there's some region in the middle that's divided by light rays, by 2 parallel 45-degree lines. Then, from this solution, we can get another solution to the wave equation, where I just scrunch this region away. Okay, so I'm just going to scrunch this region away. Out here, I'll still have x right, and here I'll have x left. But any source that I have here, I have to include on the boundary as a delta function. And is this clear why this is true? So I'm saying that this is a new space where this part is gone, but I don't have to touch the wave equation here or there. The solution is totally unchanged. All I have to do is change what the source is in the middle. And the reason is just very simple. If I look at the Gauss's law on the outside here, it tells me that this plus this minus that is that. These guys here haven't changed. All I've got to do is make sure that whatever contribution I got from here is accounted for. Okay, so I just do that by scrunching everything that I had here onto this surface. Okay, so I can scrunch solutions of the wave equation to get a new one from an old one. Okay. All right, so now, well, so far, so boring. We're just solving the wave equation in 1 plus 1 dimensions. We've decided that we're doing something on kinematic space. But as we've learned in the story of the amplitude, we have to say the word positivity for something interesting to happen. Okay, so now we're going to say the word positivity. we want the solution to the wave equation to be positive. So I want the solution that looks like du dv x equals c, where x is positive. Everywhere inside this diamond. Well, in order to define what I mean by positive, I have to tell you where it's 0. So it's a natural place to put the zeros right here at the bottom. And furthermore, remember, so it's qualitatively a lot like the other story. So there's some sort of positive region. I want the x's to be positive, and I want the source to also be positive. So I want the c to also be positive. Okay? So that's what I'm now interested in. I want to know what are the solutions of the wave equation which have this property. So I can determine anything inside here by giving boundary conditions here. Right? So if I give boundary conditions here, I can solve for any point x on the inside. That's the usual way of writing the solution of the wave equation when you give the boundary condition on like lines, right? If you give me something here, I just use the Gauss's law formula that tells me this plus this minus that is c. So if I know the boundary values here and I know the source, I determine what x is there. Okay? So, okay. Now, a little bit of thought, but I won't, it's trivial, but just believe me if you want, we'll talk about it at the end, tells us that the solution to this problem is actually equivalent to solving a slightly more constrained problem where I also say that x is equal to 0 at the top. Okay, so I'm also going to impose that x is 0 at the top. The general solution is just given by this one is a cone over this one. So once we have this one, we are done. So this is the sort of basic problem to solve. Okay. So now this is a very concrete problem. I'm solving this wave equation in kinematic space. Weird thing to do. We're solving this wave equation in kinematic space. We're just asking that x is positive when the sources are positive. Okay? And now what is this going to do? This is going to put some constraints on the boundary values here. Okay? So if here I have some, I don't know, a of u, here some b of v, I'm going to put some constraints on the allowed a of u's and b of v's that make this happen. And I want to figure out what that constraint is. So what are the allowed space of a of u's and b of v's for which this is possible? Okay? Okay, the first thing to do is to see that there are actually only one independent choice, either a of u or b of v. So let's see that. Let's see that if I shoot something out here. If this is some a here and this is some b there, then I know that a plus b minus this thing, minus that thing, which are 0, is equal to this, is equal to the total source in here. And therefore, I can determine b in terms of a. Okay, so if you give me a here, then I know what b is on the other side, or vice versa. Okay, so ultimately, in the space of all boundary conditions on one side, I want to find the positive part in the space of boundary conditions that guarantees that this wave equation is positive everywhere inside with positive source. Okay? Okay, now this problem looks too hard. So let's get an idea of what the space looks like just by sampling at a few points. So let's begin with the simplest case that we've actually done already. So let's say I have some point here, A1, and I want to know what can I say about A1? What constraints can I put on A1 such that it's compatible with what we said? Well, I'm going to shoot the light ray out of A1 and go here. So there's some B1, and we just said it. It's A1 plus B1 is equal to some C. But remember, I want A and B to be positive. So I want A1 to be positive, B1 to be positive. And so that means that in A1 space, so here is A1 space, there is some region that I have to live in. A1 has got to be bigger than 0, but it has to be smaller than C. Because here is where A1 vanishes, and here is where B1 equals C minus A1 vanishes. So the allowed values of A1 live inside this interval. Okay? All right, so let's keep going. So let's say I want to know the value of A at 2 points. Okay, so here's some A1 and some A2. Here's the corresponding B1 and B2. And here's some middle point C. Now what do I have? Now I have 3 Gauss's laws. So let me write them down. So I have this basic Gauss's law that says A1 plus C minus A2 equals 0. Okay, this one says that B1 plus A2 minus C, equals some source C equals some C prime. And this says that B2 plus C minus B1 is some C double prime, where these are just associated with, there's some C there, some C prime, some C double. Okay? So these are 3 equations and 3 unknowns for which, for example, I can imagine you're giving me B1 and B2, and I can solve for everyone else in terms of B1 and B2. And the other 3 variables in terms of B1 and B2. Solve the other way around. Let me do it this way for fun.
Do you have condition that C is greater than C prime?
Yes. The condition that all the C's are positive. Just that the C's are positive.
No, but also C is bigger than C prime.
No such condition.
So
These are just positive. Each one of these things is just positive. Nothing else. All I told you is that the source is positive inside. Nothing else.
oh, C is not the big thing. It's,
No. C is
small.
just this little thing. That's the point. This is just this thing. This is just that one. This is that one. Okay. Okay. So in fact, but
You have like a capital C and
yeah, I'm
a
sorry.
C.
Yeah, let me switch note. Let me switch notation here. Let me call this middle guy here. I don't know, middle for now. Okay.
Greek C.
So this is middle. I'll switch to better notation in a second. But then here I have some C and some C prime and some C double prime. Is that okay? Okay. All right. Now I don't have to sit here and solve the 3 equations and 3 unknowns because I can sort of more directly see what the solution is from the picture. Okay. So let's say I want to solve for what is M. Okay. Well, I solve for M just from this diamond. Well, that is one of the equations, but that's fine. So M is equal to C double prime. So from this equation, right? I want to solve everything in terms of B1 and B2. So M is C double prime plus B1 minus B2. Okay, and then I can also solve, let's say, for A2. I'm going to solve for A2. I want to know it in terms of these guys, so I'm just going to draw this big diamond, right? If I look at this big diamond, then A2 plus B2 is equal to C prime plus C double prime. There's a kind of trivial in this picture, but you see what the picture is doing is telling you how to cleverly sum the equations so you can solve for the variable, right? So in terms of the basic equation, I have to take a linear combination to do that, but the picture just tells me immediately what to do. Okay, so I get A2 plus B2 is equal to C prime plus C double prime, so I can solve for A2. A2 equals C prime plus C double prime minus B2. And finally, A1 is equal to C plus C prime minus B1. Okay? And we want all of these things, including B1 and B2, to be positive. So we want B1, B2, as well as M, A1, and A2 to all be positive. So what does this look like? So here's B2. Let me do it in B1, B2 space. The top equation tells me that I have to have, so first, B1 and B2 are positive, so we're on this side. The top equation tells me that in order for this to be positive, I have to have this guy's positive, so B1, sorry. So B2 has got to be smaller than something on the other side of this line, where this value up here is C double prime. Okay. What about this guy? It tells me that B2 can't be bigger than something. P2 is bounded up here by a line which is beyond C double prime because all the C's are positive, right? So this is C double prime, this is C prime plus C double prime. And then finally, this tells me that P1 can't be too big, and it's bounded by C plus C prime. And you see that we have to lie inside this interesting pentagon. Okay? Now, this is not an accident. This is the icosahedron. So the claim is, in general, if you just sample on endpoints and you just ask, just the answer to this question, solution of the wave equation with positive source, that the values of the x's on, let's say, on one edge, anything, are actually given, have to lie inside an icosahedron. And it's not a random realization of the icosahedron. This is exactly the realization of the icosahedron that Song and I and our friends talked about a couple of years ago. Okay? So you see, it's not just combinatorially an icosahedron. It's an icosahedron with very special properties. These sides are parallel, these sides are parallel, and so on. Okay? So it's a very specific realization of the icosahedron. And if you go to n equals 6, you'd draw an additional ring here. You'd have 9 points on the inside, and you could just go through the whole thing and see that it is an icosahedron. So why is it an icosahedron? So this is what I want to explain, and this is the entire point of this. You see, the question that I left you with at the end of last time was, we want to know what makes it obvious, what kind of question in kinematic space could make it obvious that we're looking for an object that's polytopal and that factorizes on its boundaries. Okay, that's the icosahedron. Okay? And that's exactly the thing which is not obvious from Feynman diagrams or the string worldsheet or anything like that. We want some question to ask in kinematic space that makes it obvious that you have something polytopal and that factorizes on the boundaries. We have now asked a question that's manifestly polytopal, trivially polytopal, right? We're just asking for all these positive inequalities, and we just saw it. We've plonked down all these equations, going to carve out some space. It's manifestly polytopal. The second part is to show why it manifestly factorizes on the boundaries. So this is the more interesting part. So why does this factorize on the boundaries? And let me actually say this as a statement in the continuum directly. Okay? So now I want to see what the boundary structure is. So how do I go to a boundary? Remember, what I'm trying to do is solve the wave equation with x bigger than or equal to 0, c greater than or equal to 0. So if I want to go to a boundary, I've got to pick some particular point inside and set x to 0 there. So here's a point inside, and I want to say there I've set x to 0. All right, so now there's a natural question. Where else can I send x to 0? After I've put x to 0 here, where else can I send x to 0? And, well, let's shoot the light rays out of this point. Again, this is all the only things we can do in these pictures is draw 45-degree lines. Okay, so, all right, so there's this interesting chunk of the spacetime. There's this interesting chunk of this kinematic space spacetime. Okay. Now, who are all these points? The points down here and there are the past or the future of this guy. The points out here are space-like separated, but they will never communicate with this guy before everyone dies at the top. Okay, so this is the end of space-time at the top. So no signal sent from this guy will ever make it to anything that can be affected by this guy. Okay, so they're space-like separated, but they're permanently out of touch with each other. The guys in the middle are different. They're space-like separated, but a signal from this guy can in principle make it to the future of the guy that I've set to 0. And I've drawn it this way because clearly I cannot set anyone to 0 in here. Okay? Why can't I set anyone to 0 in there? Because if I could, if I have any picture like this, where I have this point and this point are set to 0, so if this A here goes to 0 and B goes to 0, and I have some C and D, XC and XD. Then remember my Gauss's law was that XA plus XB minus XC minus XD is the source. The source was positive, so if I set this to 0 and that to 0, I have a contradiction. Okay, two negative things add up to something positive. So what that means is that I cannot put 2 points to 0 that are the corners of a causal diamond that fit inside the spacetime. Okay? And so that's everyone in here. I cannot set to 0. Okay? All right. Okay, but now this is fun because I can't set anyone to 0 in here. But in a very precise sense, I don't care about anyone in there either. Okay? First of all, if someday I need to know what some x is inside here, it's completely determined if you give me the boundary values here. Okay? If you give me the sort of boundary values on all these sides, I can fully determine what's going on in there. I can't set anything to 0 there, and therefore, what I'm trying to find out is what is the space of the solutions of the wave equation that are 0 here and positive everywhere else look like. And that space is exactly the same as what I would get if I scrunch this region away and I scrunch that region away. Okay, so what does that look like? It looks like a triangle at the top, another triangle at the bottom, and of course I have to add these delta function sources to account for the source that I have on the inside that I scrunched away. But that's what the problem looks like. So the solution of the wave equation on the support is exactly the same as the solution for these problems where it's 0 down here and 0 up there. But that's exactly the product of two problems of the same type. Okay. That's the magic. So now we've seen that we have an object that's manifestly polytopal and that factorizes on the boundaries. That's why it's the isosahedron. It's not an accident that what we get out of this is the isosahedron. Okay? Again, that's the qualitative fact we were trying to understand before. Why is this combinatorics polytopal, and why does it represent something that factorizes? And this picture of a wave equation in kinematic space with this positivity conditions put in makes both things manifest. Okay? All right. So this is the isosahedron that we talked about before. But now there's some kind of motivation for where it comes from. It's somehow associated with this wave equation in kinematic space. The kinematic space, it makes sense for infinitely many particles, right? So I'm talking about all kinematic space for any number of particles at once. Okay. All right. Now let me point out something else about this isosahedron that we'll need in a little bit. This isosahedron is naturally presented as the Minkowski sum of a bunch of simple pieces. So I just want you to see what the simple pieces look like. So what would happen? Remember, we had these. Let's go back. Let's go back to this A2 picture because I have it there. So we have this C prime, and C double prime on the inside. And let's just see what happens if I just shut off most of these C's. If I shut everyone off, this picture collapses to nothing. Okay? But let's say I just keep one of the C's and I turn the other ones off. So what happens if I set like the C prime and C double prime to 0? If I set C prime and C double prime to 0, this whole thing collapses to this line that goes all the way up to, what did I set to 0? I set C prime and C double prime to 0. So if I do that, I will get this interval. So let's say I send, so this is what I get if I send if I send C prime and C double prime to 0, and let me just set C to 1, because there's nothing else that sets any units, right? So similarly, if I look at the other one, if I send C double prime and C prime to 0, sorry, C double prime and what did I do here? C prime and C double prime. C prime and C to 0. Then I get this guy, goes from 0 to 1. And finally, if I send C and C double prime to 0, at the top, I get this triangle. Okay? And so, what is this shape? This shape is just a Minkowski sum of C1 times this interval plus, well, this C times this interval plus this C times this interval plus this C times that triangle. Okay, that's just what it means to just turn on all these C's at once. So the fact that I've presented the isosahedron as associated with the system of inequalities means that it's naturally presented as a Minkowski sum of a bunch of simple pieces. In this case, 2 intervals and this triangle. Okay, we'll use that a little bit later. All right, any questions about this so far? So we have now made it obvious that there is something that both factorizes and is polytopal, that is polytopal and factorizes. And now, on this kinematic space, we're going to ask the same question. Okay, so now the story is going to be exactly the same as the amplitude. So I have some giant kinematic space. My giant kinematic space is the space of all x's. This giant kinematic space has a positive part. This positive part, I shouldn't draw it as a ball. This is just saying all the x's are positive. Right? This is just saying all the x's are positive. So this is the positive part, just saying that all these xij's are positive, or really the x is positive everywhere inside. Okay. Now, what is my subspace? So just to be concrete, imagine that I'm fixing n. So I'm plonking down a bunch of guys here. Okay, so I'm plonking these guys. So it's really those xij's are positive. What is my subspace? I have a family of subspaces that are labeled by these C's, just like before. I had a family of subspaces labeled by this Z star that was positive. Here I have a family of subspaces labeled by these sources C. And what is a subspace? The solution of the wave equation. Okay. So the subspaces here are the solution of the wave equation. And what do I get when I take these? And that's just a stack of linear equations that defines a hyperplane. So there's this big, in this language, you have this big hyperplane, and this hyperplane is slicing through some giant simplex where all the x's are positive. And the intersection of this hyperplane with the simplex is the isosahedron. Okay. So, as promised, all the kinematic space is different, the subspace is different, but the sort of logic is very similar as the story of the amplituhedron. You have the kinematic space where the object lives, there's a positive part, there's a family of positive subspaces. The intersection of the subspace with the positive part gives you the geometry that you're interested in. And now, finally, what is the amplitude? And this is, again, the key idea, is that the amplitude is not a function. The amplitude is a differential form on this x space. Right? So the amplitude is a differential form on the space of all these x's. The amplitude is actually an n-3 form on, because the isosahedron is n-3 dimensional. It's an n-3 form on x space with the property that when you pull this form back to the solution of the wave equation, you get the canonical form for the corresponding isosahedron. So once again, we have this idea that the amplitude is a form on kinematic space. Now, again, this is perhaps slightly unfamiliar, but let's see how it works again in the very simplest example. So let's say we're doing n equals 4. Then what is it that we're saying? So if we're doing n equals 4, we have this x13 and x24. And I'm claiming the following. I'm claiming that there is a one form, which is actually d log x13. So it's dx13 over x13. It has some dx24 over x24. Okay. And in fact, there's a minus sign there. Okay. We'll see why in a second. But I claim that this form lives everywhere. It lives on x13, x24 space. Right? So this is a two-dimensional space, x13, x24. But the solution of the wave equation is the constraint that x13 plus x24 is equal to this positive constant c. Okay? So this is the solution to the wave equation here. The positive constant c, so this is the intersection. So this is the positive part. Right? This is P in this case. This is the subspace S. And they intersect on this interval. That's my associahedron. Okay? That's my, in this trivial case, my associahedron. But this form lives everywhere. This form lives everywhere. But notice what happens when I pull back this form to this subspace. It becomes dx13, let's say, 1 over x13 plus 1 over x24. Where x24, of course, happens to be c minus x13. Notice that dx24 is negative dx13. So if I put a minus sign there, I get this form, and this indeed is the canonical form for this interval. Now, why was it important that I had a minus sign here? How could I have guessed that? So first of all, I need the minus sign, otherwise I don't get the canonical form for the interval when I pull back. But there's another reason that we can see I have to have a minus sign, which is related. Something nice that happens in the case when I have a minus sign is that this form, dx13 over x13 minus dx24 over x24, is naively is a form on this two-dimensional space of x13 and x24, but with the minus sign, it's actually well-defined on the projectivized version of that space. In other words, this form only depends on ratios of the x's and not on the absolute sizes of the x's. With the minus sign here, this is d log of x13 over x24. Unless I had a plus sign there, it would not be. That's really important, because if it had a plus sign, if it was not just a function of the ratios, when I pull back to the space, it would inevitably have poles at infinity. Okay? It could not just have poles on the boundaries of the space. It would also have poles at infinity. Now, this is a really cool fact. The form that corresponds to the amplitude is actually invariant under a bigger symmetry than you realized. In other words, having a form be defined on the projectivized space means that omega satisfies that if I take the omega of the x's and I look at omega of any local rescaling, any t of the x's times the x's is equal to omega on the x's. So this is a sort of we call a projective symmetry. And I want you to notice that this is a property of the full amplitude forms, which is not true of every sort of Feynman diagram contribution at once. For example, if I took just dx over x, it's not true for 1, 3. I need both of them, and only with both of them and with the minus sign do I get something which is projectively invariant.
Why did you write T of x?
Sorry?
Why did you write T of x?
Ah, good. In order for a form to be invariant, in order for a form to be defined on a projective space, it has to be invariant under local GL1 transformations. Not just x goes to t x, but x goes to t of x x. Because I'm talking about a form, so I have to be able to compare one forms near each other, but near each other I can rescale them arbitrarily. Okay, so in order to have a form defined on the projectivized space, it needs to have this projective invariance. Okay. I should also say that, I mean, here we sort of see quickly what the Feynman diagrams are, but if I start with this wave equation, I don't see any of those things. I've just discovered this icosahedron. And if I want to find this canonical form, like always, there's all kinds of ways of doing it. You might want to, for example, get it by triangulation. And there's a very natural way of triangulating polytopes like the icosahedron that are simple. They have the property that every vertex locally looks like simplex. Then there's a way of triangulating it or getting the canonical form associated with it, which is the same thing, which is just to wedge the d log of all of the face variables that meet at a vertex and sum over all the vertices. Okay, so if you do that, you get the canonical form for the polytope when the polytope is simple, and that formula in the case of the icosahedron is known as Feynman diagrams. Okay, because every vertex is associated with a Feynman diagram. So the Feynman diagram expansion is one of many triangulations of the icosahedron. Okay? However, it's one that obscures the symmetry that the answer has. The answer has a symmetry that you don't see in any individual term in the Feynman diagram expansion, but you only see in the sum of all of them together. This fact means that there's a certain pole at infinity, which is there for every Feynman diagram that cancels in the full sum. That's the symmetry. Okay? And that is qualitatively identical to the story of dual conformal symmetry in n equals 4 super Yang-Mills. Okay, when you do BCFW recursion relations, there's a little miracle that the pole at infinity cancels. Not true term by term in Feynman diagrams, it's true because of the sum of all Feynman diagrams. And the miracle happens, we later understand, because the theory is dual conformal invariance that tells you that that infinity is not special. In momentum space, you can transfer infinity back to the origin, so there can't be any pole at infinity. Okay, there's something similar happening here, but now in dumb old phi cube theory. Dumb old phi cube theory has this hidden projective invariance, which is associated with some vanishing at infinity, which is faster than you expected. And just as with BCFW, where that vanishing infinity leads to efficient recursion relations, here too it leads to efficient recursion relations for computing this thing, which are more efficient than Feynman diagrams. Again, that's a surprise, is that you would have thought that phi cube theory is the stupidest thing in the world. You can't possibly beat Feynman diagrams. Even this thing has some symmetries that allow you to get more efficient expressions. That expose the symmetries term by term that the Feynman diagrams break. I'm not going to talk about any explicit computations, but I just want to make this, because it's a conceptual point, to say that it's not just pretty pictures, that there is a symmetry which is exposed, and that's actually associated with new recursion relations that are very efficient for getting the answer. Okay. Let me just talk for another 5 minutes, and then we'll have another break. Oh, yeah, maybe I'll just say this one conceptual thing. Another conceptual thing, and then we'll pick up with more details when we come back. Let's compare the story that we saw this morning to what we've seen this afternoon so far. Okay, so this morning we talked about the kinematic space for n equals 4 super Yang-Mills, just the space of n 4 vectors, right? And then there was a sort of fancier thing that we did there with all this positivity and winding, blah, blah, blah. But there's a positive part, there's a subspace, there's that intersected the positive part gave us the amplitudehedron, and the amplitude was the form on kinematic space that pulled back on the subspace to be the canonical form for the associated geometry. Identical story here, right? So we've said that already. The only thing all the actors are different. The kinematic space is different, the definition of the positive part is different, but it's the same thing. There's a big positive part, there's a subspace, we pull back to the subspace, we reveal the form. In my colloquium, in order for both people who have not been coming to the workshop and workshop people not to be the overlap not to be maximally bored, I will talk about another subject which we have not talked about at all in this workshop, but which I feel very strongly is going to be important in the future, which is the analog of all these things in cosmology. Okay, we'll see exactly the same things. A positive part, a space, pull back, exactly the same story. At least the beginning of the same story for seeing these things happen in cosmology. But let's stick with these things that we've seen in amplitudes. There is something interesting, which is So we've seen this idea that the amplitude is a form on kinematic space. But we've seen sort of two avatars of it. So one of them we've seen in the case of the amplituhedron. So here, what is the form about? Here, the form part we saw was sort of about helicity. In other words, we took these etas of Susie and we replaced them by dz's. And we know that the etas of Susie are keeping track of helicity information. So these forms, if you like, the components of these forms are unifying amplitudes that have different helicities together. In fact, this is something you can do directly with ordinary momenta and ordinary spin helicity variables, lambda, lambda, tildes, and so on. This is something you could do in the standard model. This is something that would be an open problem that's, I think, very interesting to explore. We could take QCD, pure standard model, okay? And instead of unifying all the different helicities together using the polarization vectors the way we normally do in quantum field theory, we can just take, let's say I have gluon amplitudes, I take a negative helicity gluon amplitude, and I make a form out of it by wedging with d squared lambda tilde. And I add something with a positive helicity amplitude, and I make a form out of it by wedging with d squared lambda. Okay, and I just keep going. So in this way, I can take just in standard model processes, all the amplitudes are actually unified together, glued together into a differential form that's defined on the lambda lambda tilde space of all the massive particles. We can even do it with massive particles using the analog of the massive spin helicity formulas. Okay, so this idea that the amplitude is a form is just an interesting bookkeeping device to begin with, just to unify different helicities objects with each other in a canonical way. And then you can begin to look for geometry by looking for residues and singularities and poles and so on with all the advantages of having the form at our disposal, just as we saw for n equals 4 super Yang mills. In fact, you can do this for n equals 4 super Yang mills itself back in lambda lambda tilde space, and this is something that Song and Livia and Tomek have been doing to find a momentum space version, a lambda lambda tilde version of the amplituhedron. And something seems to exist, at least at tree level, directly giving us differential forms in lambda lambda tilde space, and that is giving us the way of keeping track of the helicities, or the etas, again, just as we did in ordinary momentum twister space. Okay, so that's one thing. On the other hand, we've seen this other thing, which is that we have these sort of DS's, or these DXIJs, or these are sort of the D of Mandelstam invariants, however you want to think about it. Now this is a little more peculiar. What are these keeping track of? Okay, so this is not so obvious what these are keeping track of. We just did it, it's fine. But here they really had a purpose in life. They were keeping track of helicity. Here it's less obvious what they're doing. But in fact, you don't really see it if you just draw planar diagrams. But it turns out there's something very interesting. And if you draw arbitrary non-planar diagrams, any old diagrams at tree level, then if you wedge together the Ds of the propagators that occur in the non-planar diagrams, that those objects satisfy exactly the same identities as color Jacobi factors that you would associate with the state of diagram. So this is at least a partial answer to these questions, that these forms in kinematic space somehow know about color. It's absolutely bizarre. It's absolutely bizarre. We don't know how these two ways of thinking about things are related to each other at all. We have this sort of strange embarrassment of riches that we have one way of making amplitudes into forms that keep track of helicity. We have another way of making amplitudes into forms that actually keep track of color, even though I have not really talked about that because we've only seen things in a single, we've only talked about a single color ordering. So trying to find some way these things are related to each other is a very interesting question. And certainly one beginning would be to try to go back to, for example, we can try to start from the momentum amplituhedron and see how we can scale out the helicity dependence from the lambda and lambda tilde variables and just be left with something that depends on Mandelstam's. And see if in that way we can go from the forms that are defined on the amplituhedron space to pieces that pick out the helicity components and other pieces that only depend on Mandelstam's, at least in 4 dimensions. Okay? So it's not obvious how that will connect to the story, which doesn't know about 4 dimensions, but that's at least one direction we could try to make. A connection. And finally, let me say something a little simpler. So going back, in the second discussion, we motivated everything by this sort of invitation that you're the simple-minded experimentalist at infinity. You're moving around these Mandelstems. You notice this interesting pattern of poles. That pattern of poles is dead universal for any theory, right? Any theory has that interesting pattern of poles. Any planar theory has that interesting pattern of poles. And you find the pattern is polytopal, and that's the isosahedron, right? Okay, so in the morning we're talking about the amplituhedron, which is about gluons. So how are these things related to each other? Well, what's going on is the following. Every theory in the world, every planar theory in the world, has this pole structure that we've seen for the isosahedron, right? Because that's what we get from these cubic graphs. However, the theory of gluons has more. The theory of gluons, to a physicist, has more singularities. They're not just propagators going on shell. We have these soft singularities. Okay? Now, this is something which, in the conventional ways of doing quantum field theory, you punt to the polarization vectors. The things that, as on-shell amplitudologists, we hate these polarization vectors sometimes, okay? And that's one reason we hate them, is that a lot of physics is shoved into those polarization vectors we don't see. All we see in the Feynman diagrams are the obvious collinear singularities. We don't see the soft singularities in our face until we actually write things completely invariantly in terms of lambdas and lambda tildes. When we do that, we see there's more singularities we can take. For example, for the 4-particle amplitude, the 4-particle amplitude naively only has one pole that we can take, so you would associate it with a one-dimensional object. That's why we drew this little isosahedron, this little interval. But the actual amplitude for gluons, the Park-Taylor formula, has 4 poles downstairs. And as you take all the residues on those poles, you discover a kind of intricate structure, which now we know is the facet structure of G24. So once you include soft singularities, you see more than just these factorizations. And that singularity structure is not polytopal. Okay, so somehow adding the soft singularities takes us from something which is captured by the combinatorics of the isosahedron to something that needs Grassmannian combinatorics in order to capture. So that's what the amplitude, so purely at the level of the singularity structure that's being captured by the geometry, what's going on with the amplituhedron is we uplift everything into the Grassmannian because it's necessary in order to see all the singularities, which generic theories don't have. Okay? Of course, the amplituhedron has all the ones that generic theories have, but it has more. And that's what's being captured by the richer Grassmannian geometry. String theory, the classic string worldsheet, doesn't know about this. Okay? It treats it just like everything else does. It has polarization vectors, and so you have to work and hunt to discover them. Okay? So if you want to sort of fully geometrize or combinatorialize the singularity structure of the amplitudes for gluons, you're forced to go into this Grassmannian direction. Yes?
Sorry. So what you described with the 4-particle amplitude,
Yes.
I understand, because like if you
Yes.
factorize like in the soft limit, you would factorize in a 3-particle amplitude, and
Yeah.
you would need complex kinematics for this. So lambda tilde space is very natural. But normally I get with Weinberg's soft factor, I see that there's a soft pole in 1/q. And there I can write that in d dimensions, and I have a polarization vector upstairs. So what exactly did you mean you don't see the soft pole?
No, of course you see the soft pole, but you don't see what the boundary structure is associated with the soft pole. That's a problem. All you see is this stupid pole. You don't see that stupid pole is resolvable in all these ways, with lambdas becoming parallel, lambda tildes becoming parallel, and so on. Okay? So it's as if you had the positive Grassmannian. It's as if you just had the lambdas and lambda tildes. You just had G24, but you didn't see that you're allowed to do all these sort of very detailed things where 2 things are on top of each other, then you send one thing to 0 while you keep the other one finite, and so on, right? So all of these things, which to a physicist look like extremely degenerate configurations, which you might be tempted to ignore and you don't even see when you use polarization vectors. I want to stress you don't even see them when you use polarization vectors, because all you ever see is the part that's symmetrical in lambda tilde. You don't even see the holomorphicity when you use polarization vectors.
Yes,
Okay,
chiral
so
nature.
it's the chiral nature. It is the chiral nature, and those are the things which are missing. Surely there's something like that in higher dimensions too. gluons because this physics is universal for gluons. But, by the way, we don't have to go all the way down to something as delicate as that. You can even take just a box, just a one-loop box integral, and that too you say, this is very cool. I realize it's for d-logs. I really like these d-logs. I want to explore what the singularity structure of these d-logs are. And if you do it, you find you can't express it in some polytopal way. It's G24 again. Right? With massless corners on the outside, it's G24 again. But if you really want to take into account collinear and soft singularities, you have to enrich, go beyond what we just see with factorization to something that has the Grassmannian structure. Yes?
So, as you know, the association can be thought of as the tropicalization of the positive G2n.
Right.
Is this Grassmannian structure related to the other positive Grassmannian structure that we see?
That is a wonderful question, and I might have something to say about it if we get there. Well, the short answer is we don't know for sure, but this is the kind of zeroth order story. Is that once we start talking about, well, I won't say the word tropicalization, but I'll be doing it. Okay? Once we do that, then all of these things start living in the same space. We have G2n mod torus, G4n mod torus. Every actor in this world, now we're doing the same things with them, but just asking slightly different questions about them. Okay? And so I don't know very precisely how they'll be linked, but they're all definitely in the same playground now. I mean, not just sort of far away. They're absolutely in the same territory. That's part of the thing that's fun right now, right? That these three subjects, we haven't gotten to the string amplitudes. We'll get there when we start again. But that n equals 4, these bi-adjoint field theory amplitudes and string amplitudes are now in the same ballpark of ideas. All right. When should we reconvene?
I don't know, maybe 310?
3:10. Is that okay? All right. Great.